Okay, so it's my great pleasure to have William Gvozdjak from MIT Prime and Bellevue High School. And today he will talk about the classification of low rank hot dimensional modular categories. So please, William.
Thank you very much for inviting me. My name is William Gvozdjak. I'm currently a rising senior, so rising 12th grader at Bellevue High School in Bellevue, Washington, in the United States. I'm also a student researcher at MIT Primes USA. So thank you very much to the MIT Primes program for making this possible. It's a research program for high school students in the United States. Um, this is a joint work with Augustina Chanke, who is a PhD student at the University of Oregon, as well as Professor Julia Plavnik, who is at the Indiana University at Bloomington. So today I'm going to be presenting on the classification of low-rank odd-dimensional modular categories. I'm going to be following the paper we put out on arXiv. The arXiv number is listed here. So first, before I get into the actual results, I'll first present some motivation for the question that we were trying to answer. So in general, the overarching question that surrounds this field is, can we classify fusion categories by rank? And when I say rank, I mean the number of simple objects in the fusion category. So are we somehow able to figure out what all the possible fusion categories are for some given rank? And this question is quite difficult to answer in general if we're trying to answer it for a fusion category in general. And this can be seen here in this first bullet point. Currently, we only have classified fusion categories up until rank 2, which is a result from 2003 by Ostrich. But adding additional structures and properties to these fusion categories can usually make this problem much more approachable. So we can see here in the second bullet point that if we add a pivotal structure to our fusion category, then we are able to classify them up until rank 3. If we add, if we make a pre-modular category instead of a fusion category, then we're able to classify it all the way up until rank 5. If we further require that it's an integral modular category, so we have the property that it's integral, we're able to classify them up until rank 12. And if we add the property additionally that the integral modular category also has to have an Odd-Frobenius parent dimension, which are the algebraic structures that we researched in our research, we're able to classify them up all the way until rank 15. And that was due to a recent result in 2022. So yeah, you can see here that adding additional structures and properties makes this problem much more approachable because as we go down this list, the that we're able to classify these fusion categories to definitely increases. So now I'll get into our actual research question that we were answering. Before I do that, I'll first present 3 theorems that are relevant. The first one is called the rank finiteness theorem for modular categories. And it states that there are finitely many modular categories of fixed rank up to equivalent. So this makes the question of classifying modular categories much more approachable because we know that there are not potentially an infinite number of modular categories for a given rank. So yeah, we're able to actually figure out what those finitely many modular categories are. These next 2 results are recent results in the classification of odd-dimensional modular categories. The first, both of them are come under the bullet point that we saw on the last slide. So the first one states that all odd-dimensional modular categories of at most 11 are pointed. So why is it interesting? Well, we know we have fully classified all odd-dimensional modular categories that are pointed. Because pointed modular categories, as we'll see in a future slide, are fully classified by finite groups and 3 cycles. So we've successfully classified all odd-dimensional modular categories of rank at most 11. Additionally, in this paper, Briard and Rao demonstrated a non-pointed example of an odd-dimensional modular category that was of rank 25. And it's this category here. It's the representation of the double of the semi-direct product of Z7 and Z3. And this is interesting because this is kind of the lowest rank odd-dimensional modular category that is kind of unique because up until this point, all of the modular categories that we knew existed of rank at most 25 were all pointed. And pointed categories are, as I said, fully classified, so a little bit uninteresting. Now, Briard and Rowell demonstrated this non-pointed example of rank 25, which is kind of a unique occurrence. So this does actually naturally give rise to the question, well, is this the lowest rank odd dimensional modular category that is pointed? Yeah, so that is one part of the question, main question that we will be trying to answer. Finally, this theorem was proven recently, a few years ago, by Chankey and Plavnik. It states that all odd dimensional modular categories of rank 13 and 15 must be pointed. So first, this extends the classification of odd dimensional modular categories to rank 15, as we saw in the previous slide. They also showed that odd dimensional modular categories of rank between 17 and 23 must be either pointed or perfect. And we'll see this later in the preliminaries, but perfect is essentially a category that's on the complete opposite of the spectrum from perfect categories are not fully classified. So according to this theorem, if we do somehow show that odd dimensional modular categories cannot be perfect, or we do fully classify odd dimensional modular categories that are perfect, this would extend classification of odd dimensional modular categories up until 23. So yeah, this gives us the main question that we were trying to answer. Are odd dimensional modular categories of rank less than 25 necessarily pointed? So again, discarding the perfect case for these four ranks would answer this question. So next, after that, after the motivation, I'll get into some preliminaries for understanding the results. Before I do that, we first let K be an algebraically closed field of characteristics 0 throughout this presentation and our paper. So first, I'll define a tensor category. We say that a tensor category C is a category that has two main structures and then one condition. The two main structures are an abelian structure and a monoidal structure. The abelian structure essentially allows us to take direct sums of any two elements, of any two objects in our category. So the way we do this is for any object, we require that there exist short exact sequences, kernels and co-kernels. I won't go into the details about the actual definition in this presentation. In addition to the abelian structure, we also require that a tensor category is k-linear. So this means that for any two objects in our category, the Hom space between those two objects must be a vector space over our base field K. We also say that C must be locally finite. So in addition to requiring that the Hom space between any two objects is a vector space over K, we also require that those Hom spaces are finite dimensional vector spaces. Then for a tensor category, we also require that it has a monoidal structure. So we already introduced direct sums of any two elements. Now we'll introduce tensor products of any two elements. And we'll do this by creating associativity that has to satisfy the pentagon axiom, as well as introducing the unit object 1 of the category and unit isomorphisms that go along with it. We further require that a tensor category must be rigid. This means that there have to exist left and right duals in our category. Along with these left and right duals, we also receive co-evaluation and evaluation maps that will come in handy in a later definition. Finally, we also require that a tensor category satisfies this compatibility condition. So we require that the endomorphism algebra of this unit object 1 is equivalent to our base field K. And this is the same as saying that our unit object 1 is a simple object inside of our category. And this is called the compatibility condition because it essentially ensures that our abelian structure is compatible with our monoidal structure. Because as we'll see later, the simple object is kind of an abelian concept and the unit object is a monoidal concept. And we require that they kind of work together. So here I have listed two examples of tensor categories. The first example is the category of G-graded vector spaces along with the 3 cocycle omega. And the second example is the category of the representations of a group G. Next, I'll define fusion categories. This To do this, we'll first define what a simple object is inside of our category, which we were talking about in the last slide, as well as what a semi-simple tensor category is. We say that an object in a tensor category C is simple if it doesn't have any sub-objects. So this essentially means that we're not able to write this object as the direct sum of any other objects. So it's kind of the most simple that you can make it in terms of the direct sum. Our tensor category C as a whole, we say it's semi-simple if every object inside of our tensor category can be written as the direct sum of simples. So if we have a semi-simple tensor category C, then there exists some potentially infinite set of simple objects inside of our category that if you take all the direct sums of these simple objects, you're able to create every single element inside of our category. So for a fusion category, it's a tensor category, and we not just require that it's semi-simple, so it satisfies this condition that you can take the direct sums of all the simple objects to make every single object. But we also require that there are finitely many simples in our fusion category. So there's some finite set of simple objects in our category, and we can make every single object using those. So here I have two examples that parallel the examples that we had for tensor categories. Again, we have the category of G-graded vector spaces with a 3 omega, and the category of the representations of a group G. But now we require that our group G is finite, so that we satisfy this condition that there are finitely many simples in a fusion category. Given that we have finitely many simples in a fusion category, it's fairly natural to ask how many simples are there for a given fusion category. So this gives rise to the definition of a rank. We say that the rank of a fusion category is just the number of simple objects it has. So when we say that we're classifying fusion categories by rank, as I said in the first few slides, this means that we're asking for a given number of simple objects, are we able to figure out what all the possible fusion categories are? I will also define the Frobenius parent dimension. This is a really useful concept because it allows us to use a variety of number theoretic arguments on a fusion category that tell us things about the category itself. The Frobenius parent dimension, as we'll see on the next slide as well, is a really nice invariant that tells us things about the category. So first to define this, I'll define the Grothendieck ring. So we say that the Grothendieck ring of a fusion category is the free abelian group generated by all isomorphism classes of simple objects in C. So when we make the Grothendieck ring, the abelian structure of our fusion category, so the direct sum, gives it the structure of a group. Then when we introduce the monoidal structure into our fusion category, this gives it the structure of a ring. And finally, also, if we go into details, the rigidity of a fusion category gives it the structure of a fusion ring, which is one thing that the Grothendieck ring is. So essentially what the Grothendieck ring does is that it takes our fusion category C and it removes and it forgets kind of all of the categorical concepts that are attached to the fusion category, and it reframes it in terms of a ring. And this allows us to use all of the traditional things that we can use on a ring on this Grothendieck ring, and then we can kind of apply those concepts back onto the fusion category itself. And this is exactly what we do when we define the Frobenius parent dimension. So we say that the Frobenius parent dimension is the group homomorphism that goes from the Grothendieck ring of C to the real numbers. And it's defined for a basis element X as the maximal real eigenvalue of the matrix of left multiplication by X. And then we do this translation back into our fusion category. So we say, in a fusion category, the Frobenius parent dimension of a simple object X is just the Frobenius parent dimension of X in the Grothendieck ring of C. Then for the actual category as a whole, we define the Frobenius parent dimension of C as a category to be the sum of the squares of the FPDIMs of all of the simple objects X in the category. So why do we really care about the Frobenius parent dimension in the first place? Well, one of the few reasons that we care about it is that it satisfies a bunch of really, really nice properties. And these properties make it so, for example, if we have an equation in terms of the in terms of the objects inside of our category, one thing that we're able to do is we can take the Frobenius pairing dimension of both sides, and this leaves us with an equation purely in terms of real numbers. And then we can use a lot of number theoretic arguments to actually infer things about the Frobenius pairing dimensions in the category. And using these, we can then actually go back to the category itself and say things about the category. So what are these nice properties? Well, the first one is that when we defined a fusion category, we did define the unit object 1, and we would hope that this does work well with the Frobenius pairing dimension, and it does. So the Frobenius pairing dimension of our unit object 1 is just 1, which is the unit object of the real numbers in terms of multiplication. A fusion category is also rigid, so we would want the FPDIM to work well with the rigidity and the duals, and it does, because the FPDIM of any object X is the FPDIM of its dual. Finally, the FPDIM works with the two main operations of our Grothendieck as well. So if we take the FPDIM of the direct sum of two objects X and Y, this is equal to the sum of the FPDIMs of X and Y individually. And also similarly, FPDIM of the tensor product of X and Y is the product of the FPDIMs of X and Y. Additionally, one other reason that we use the Frobenius pairing dimension is that it's a really nice invariant in our categories. So using the FPDIM, we can infer a lot of things about our category. So for example, one thing is if the FPDIM of an object is 1, then we know that that object must be invertible, which I will define on a future slide. Also, whether or not a category is integral, so whether all the FPDIMs of its simple objects are integers, tells us things about whether it comes from, for example, a quasi-Hopf algebra and things like this. Next, I'll define a weakly integral and an integral fusion category. So we say that a fusion category C is weakly integral if its Frobenius pairing dimension is an integer. And we say that our category C is integral if the Frobenius pairing dimensions of all its simple objects are also integers. So one thing to note here is that it is true that integral does imply weakly integral for a fusion category. And it's easy to see this because we define the Frobenius pairing dimension of C as the sum of the squares of the FPDIMs of all the simple objects. So if all the FPDIMs of the simple objects are integers, then we know that the FPDIM of C is also an integer. But one thing to remember is that if a fusion category C is weakly integral, it doesn't necessarily imply that C is integral. And we can see this in an example here. Tambara-Yamagami categories are defined where their simple objects are the elements of an abelian group G, as well as some element X that's not inside of our group G. And then because our category is semi-simple, this allows us to get every single object in our category by taking direct sums. So we simply have to define the tensor product in the Grothendieck ring. So we say if we have two elements of our group G, G and H, and we take their tensor product, this is defined to just be the product of G and H inside of our abelian group. If we take an element of our abelian group G and take its tensor product with our element X, this is defined to be X, and the same is for vice versa. So X tensor product G is just X. And finally, we define the tensor product of X with itself to be the direct sum of all of the G's in our abelian group G. So now we actually look at the Frobenius pairing dimensions of all of these simple objects and also the category as a whole. So the FPDIM of every we know that the FPDIM of every single simple object that comes from this abelian group G is just 1. Now, if we look at the FPDIM of this simple object that's not from this abelian group, which we can find using this last equation here, if we take the FPDIM of both sides, we end up with FPDIM of X squared equals the order of G. We then end up with that the FPDIM of X is equal to the square root of the order of G. So immediately here we can already see that if the order of G is not a perfect square, then the FPDIM of X will be irrational, and therefore our fusion category C will not be integral. But we can see that C will necessarily be weakly integral, because if we actually compute the Frobenius pair dimension of the whole category, it ends up being 2 times the order of G, because the simple objects from our abelian group G contribute 1 times the order of G, and then this element X also contributes 1 times the order of G. And since the order of G is an integer, the FPDM of C is an integer. So yeah, Tambara-Yamagami categories are an example of fusion categories that are weakly integral but not integral. Next, I will define this concept that we were seeing in the first few slides of the preliminaries. It's this idea of Vect G to the omega. We say that Vect G to the omega is the category of finite dimensional G-graded vector spaces. The objects inside of this category are vector spaces V that have this additional structure of a grading. So we can decompose V into some direct sum of vector spaces V sub G for every single element G of our group G. In this category, our simple objects are going to be one-dimensional vector spaces. And these one-dimensional vector spaces are going to be concentrated in some certain degree of our group. So we can see down here that the unit object is going to be a one-dimensional vector space that's concentrated inside of degree E. So degree the identity of our group. Every single other degree has one simple object inside of it. That corresponds to that degree. We also define the tensor product. So the component corresponding to the element G of the tensor product of vector spaces V and W are defined by this formula here. So we go over every single elements X and Y of our group, such that XY equals G, and then we take the tensor product of the component of V corresponding to X and the component of W corresponding to Y. Finally, we also have to define associativity. So one interesting thing to note here is that in this category, associativity doesn't necessarily have to be the intuitive trivial associativity. And the way we define associativity inside of this category is using a 3 cocycle, because that determines this. Next, I'll define pointed categories, which come up repeatedly inside of our work and in previous classification. We say that first I'll define invertible objects actually. So we say a simple object X inside of our fusion category is invertible if both of its evaluation map and its co-evaluation map are isomorphisms. So the evaluation map, which goes from the dual of X, tensor product X, to the unit object 1, and the co-evaluation map, which goes from 1 to the tensor product of X and X dual. They both come from the fact that our fusion category C is rigid. And if both of these maps are isomorphisms for our simple object X, then we say that X is invertible. And as I said earlier, this is equivalent to saying that X is invertible if and only if its Frobenius pair dimension is 1. So this is really, really nice, because if we have the Frobenius pair dimensions of all of the simple objects inside of our fusion category, then we can immediately tell which of those simple objects are invertible, just by looking at whether their FPDMs are 1 or not. We define the group of we denote the group of isomorphism classes of the invertible objects in C as G of C. And it's not hard to check that this is actually a group, that it satisfies the group axioms. We say that a fusion category is pointed if all of its simple objects are invertible. So in terms of the Frobenius pair dimension, if we look at all of the Frobenius pair dimensions of all the simple objects and they are all 1, then we know our fusion category is pointed. And one interesting thing to note about this is that because all those FPDMs are 1, in a pointed fusion category, the rank of the category is going to be equal to its FPDM because of the way that FPDM is defined. And as I said earlier, pointed fusion categories are fully classified. And this is because if C is a pointed fusion category, then C is equivalent to our category of finite dimensional G-graded vector spaces. And these And these categories are classified fully by finite groups G and 3 cocycles omega. And because these are fully classified, this means that pointed fusion categories are also fully classified. We say that a fusion category is perfect if its only invertible simple object is 1. This is kind of on the other end of the spectrum from pointed, because we say that a category is pointed if it's all of its simple objects are invertible, and it's perfect if the absolute minimum number of simple objects are invertible. We do know that the unit object 1 must be invertible, because as we said in an earlier slide, the FPDIM of the unit object is 1. That's one of the properties of the FPDIM, which means that 1 must be invertible. Next, I'll define the universal grading. We repeatedly use the universal grading throughout our work because it provided an easy way to kind of look at, to kind of split the simple objects into different components of the grading. And we could infer things using that. So we say that if G is a finite group, then a G grading of a tensor category C is some decomposition of C into components C sub G, which is obviously graded by G. So for every single G in G, such that C sub G is abelian. So for every two objects inside of C sub G, we can take their direct sum, and this remains in C sub G. And the tensor product also satisfies this really nice property, that if we have an object in C sub G and an object in C sub H, we can take their tensor product, and this lands us in C sub GH. So this means that the tensor product works really nicely with the structure of the group. One thing to note is that these two conditions do also imply that our unit object 1 is inside of C sub E, so the component of our tensor category that corresponds to the unit the object E inside of our group, and also the dualizing functor inside of our category maps a component C sub G to the component C sub G inverse. So the dualizing functor also works really well with our G grading. We say that a grading is faithful if all of the components of our grading are non-zero. So this essentially means that if we have a faithful grading, every single component provides us with new information. Finally, we define the universal grading. So we say that if any fusion category C admits a canonical faithful grading called this universal grading. And one of the interesting things about the universal grading is that its trivial component is the adjoint subcategory C sub AD of C. And this is interesting because the adjoint subcategory is actually defined outside of the context of the universal grading. It's defined to be the subcategory of C, the fusion subcategory of C, that is generated by taking X tensor X dual for every object X in C. Additionally, if C is modular, then its universal grading group is the group of invertibles G of C, which is really nice because if we know the number of invertibles inside of C, this tells us a lot of stuff about the universal grading of C. Finally, we define modular categories. So we say that C is a modular tensor category if it satisfies these four conditions. C has to be fusion, so it has to satisfy all the rules that we discussed in previous slides. It also has to be braided. So what this essentially does is it makes the tensor product commute in a coherent sort of way. And it does this using the two hexagon axioms. C has to also be spherical. So for every object X, there has to be some isomorphism between X and its double dual. And the quantum dimension of X has to be equal to the quantum dimension of its dual. If C satisfies these first three conditions, we say it's a pre-modular tensor category. And then finally, if C satisfies this non-degeneracy condition, we say it's a modular tensor category. So what is this non-degeneracy condition? The sphericality of C allows us to take traces inside of our category, and using these traces, we can define what's called the S matrix. And if our S matrix is non-degenerate, then we say that C is non-degenerate as well. Yeah, so this was overall a very high-level definition of a modular tensor category. Next, I'll get into some previous results that have been shown about modular categories. This first slide are kind of general results that are useful in the classification of modular categories. So this first theorem I already discussed in the motivation is the rank finiteness theorem for modular categories. It states that there are finitely many modular categories of a given rank up to equivalence. One interesting thing about this is that if we go into a more general space, it's known that this rank finiteness theorem is actually known for G-crossed and braided fusion categories, but it's not known for fusion categories in general. And it's shown in a paper labeled JMNR. Additionally, we have this theorem that is really useful. It states that if we have an integral modular category C, then its Frobenius parent dimension is odd if and only if C is maximally non-self-dual. So when I say maximally non-self-dual, this means that every single object that's not the unit object has a dual that's not equivalent to itself. So we do know that the unit object is dual with itself, but if every single other object has a dual that's not itself, then it's maximally non-self-dual. And this is useful because essentially this means that we can pair up objects inside of our modular category. For example, in our Frobenius parent dimension, we know that the FPDIM of any simple object X is equal to the FPDIM of its dual X dual. So if we have a maximally non-self-dual modular category, we can pair up Frobenius parent dimensions because we know that they're going to be duplicates. One interesting thing about this is that also if the Frobenius parent, it's known that if the Frobenius parent dimension of C is odd, then C must be integral. So if we have a modular category that is odd dimensional, then it must be integral as well. We also know that if we consider the universal grading of an odd dimensional modular category C, then the ranks of all the components of the universal grading must be congruent to each other mod 8. So this is really useful because if we're considering the universal grading of our modular category C, this helps us to determine with much greater certainty what the actual ranks of the components of the universal grading are. Because without this, there would be many, many more possibilities for what the ranks of the components would be. But given that we know they're mod 8, it's much more feasible to list them all out and perform casework on them. Finally, we know that in a weakly integral modular category C, for every simple object X, the ratio of the Frobenius parent dimension of C, the category C in general, divided by the square of the Frobenius parent dimension of the simple object X must be an integer. So this is really useful because it greatly restricts what the possible values of FPDIM X are. Because otherwise, we would solely know that the FPDIM of X is some integer whose square is less than or equal to the FPDIM of C. But with this, we know that its square even has to divide the FPDIM of C. One thing to note is that if we do remove this weakly integral condition from this lemma, so we solely require that C is a modular category, instead of knowing that this ratio is an integer, we know that it's an algebraic integer. Here are some previous results for classification that are sorted by chronologically sorted. All of these produce new results for modular categories with additional both structures and properties added to them. And so we can see here that I think a few decades ago, it was shown that unitary modular categories of rank at most 4 they were fully classified. Additionally, non-self-dual modular categories of rank at most 5 were classified, and so on. You can see the history of odd-dimensional modular categories here as well, which were the algebraic structures of interest for us. I think in the early 2010s, it was shown that odd-dimensional modular categories of rank at most 11 were classified, as we said in the motivation. And then a couple years ago, odd-dimensional MTCs of rank 13 and 15 and partially 17 to 23 were classified. So now we'll get into our actual results that we used. So In general, the strategy that we use to tackle the cases of rank 17 to 23 um, was a computational strategy. So we created an algorithm and wrote code in order to try and solve the cases for us. So what did this algorithm do? So it was a recursive algorithm that, given the rank of a modular category, odd-dimensional modular category C, and the number of invertible objects in the category, the algorithm desired to output the dimensions of the simple objects in the modular category. Usually there were more than one cases if it did finish, so there were multiple possible sets of dimensions that would work. But in those cases, we would just work through all those cases and try to discard. So how did it do this? Well, it used the equation for the Frobenius pair dimension of the category C as a whole. So we know that the FPDIM of C is the sum of the squares of the FPDIMs of all of the simple objects inside of our category. So this first term, the order of our group G of C, comes from all of the invertible objects in our category because they all have FPDIM 1. And then because we know our MTC is also odd dimensional, we know that it's maximally non-self-dual, as I said earlier, which means that we can pair up all of the remaining dimensions. So that's where all these coefficients of 2 come from. What our recursive algorithm did was every time we recurse to a new depth, we would try and remove one of these unknown variables. Until at the very end, we would obviously be left with just one unknown variable, which we could actually solve for. The way we did this reduction of variables was by using this idea that we saw in a few slides ago, that the FPDIM of our modular category C is some integer multiple of the square of the individual dimensions. So it's equal, the FPDIM of C is equal to some m sub I times d sub I squared. And what this did was that it not only let us express one dimension in terms of the previous dimension, because we can write a sort of chained equation using this, because we can write the same thing for the next dimension. But it also greatly restricted what the possible values of m sub I are, because we know that it has to be the FPDIM of C divided by the square of some dimension. Now, I would say the biggest thing that this algorithm did to actually tackle these cases was this optimization. Because if we just ran this algorithm purely like this, I don't believe that it actually finishes in a reasonable amount of time for the ranks of interest. So we optimized this algorithm by noting that the largest square free divisor of each m sub I must be the same. And the way we prove this is we use this chained equation that we saw earlier. And there is a number theoretic argument that can show this. So this is really, really nice because it means that if we determine what the value of m sub 1 is in the very beginning of the algorithm, this means that we have already determined what the largest square free divisor of every single m sub I is for the rest of the algorithm. So what this reduces this algorithm to do, into doing is just determining what the remaining square portion of each m sub I is. And this is much, much faster because we only have to try all the perfect squares that in some range instead of trying every single possible value. This algorithm also extends a technique from the paper by Chenky and Plotnik. The technique in that paper was handled manually. So what we did is we generalized it into an algorithm so it would be able to run much faster. And also, one reason why it had to run faster was because we handled the case when an m sub I is not square free. And this is interesting because when m sub I is square free, this ratio m sub I plus 1 divided by m sub I is necessarily an integer, which means that when we substitute in to remove an unknown variable from this equation, all of the coefficients remain integers. And this means that the equation is much, much easier to work with. But when m sub I is not square free, this ratio is not necessarily an integer, which makes dealing with the equation much harder. So what we did is we converted this technique into an algorithm, and we also allowed coefficients to go into non-integer numbers. And yeah, that was what our basic algorithm did. However, when we went into much higher ranks, so when we started pushing into ranks that were much larger than what we started with, our basic algorithm started not being able to finish in a reasonable amount of time either. Because in higher ranks, there are obviously more simple objects, which means there are more unknown dimensions in our equation. So because of this, there were the depth that the recursion had to go into was much, much higher, resulting in the algorithm taking an unreasonably long amount of time to finish. So one way that we tried to tackle this problem was by introducing this new algorithm called the adjoint algorithm. And the adjoint algorithm was very, very similar to our basic algorithm, but it was different because it only computed dimensions for simple objects inside of the adjoint subcategory. So you can see here that the initial starting equation followed a really similar format, but the only difference is that we are considering exclusively dimensions and simple objects inside of the adjoint component. And what this does, obviously, is that in the adjoint component, there are fewer simple objects, which means that there are fewer unknowns, so the recursion has to go to a smaller depth. So it has a higher likelihood of finishing in a reasonable amount of time. So to kickstart this algorithm, in addition to the rank and the number of invertibles in C, we also had to provide the rank of the adjoint component in the universal grading and the number of invertible objects in that adjoint component. So yeah, as I said, the basic algorithm may not always finish in a reasonable amount of time, but the adjoint algorithm has fewer dimensions to run, so this expands the number of cases that finish in a reasonable amount of time. And the adjoint algorithm, obviously, if it does finish, it provides us with a little bit less information than the basic algorithm would, because it does output fewer dimensions. But oftentimes, this number of dimensions was still sufficient to actually discard the case. In addition to these computational techniques, we also showed a few mathematical results that were more general in order to actually manually discard cases, because oftentimes, if we had a case, it was easier to just discard it mathematically than having to run the whole algorithm for it, obviously. So these were a few of the results that we had for that. So the first one, we showed that in an odd dimensional modular category C, its rank must be some non-negative integral linear combination of the number of invertibles in C and the number 8. So what this does for us is that it makes the possibilities for the number of invertibles inside of C much, much smaller. Because without this result, we know that the number of invertibles, all we know about the number of invertibles is that it's at most the rank of C. But with this result, it's much more feasible to actually list out all of the possible number of invertibles and perform casework on it. Then we also showed that if C is a modular category that satisfies this condition, then if we consider the action of the invertible objects of C on the simple objects of C, then we know something about when a simple object can be fixed by this action and when it can't be. And this is useful because considering this action actually gives us a lot of information about the Frobenius pair dimensions. Because, for example, if a simple object X is not moved, it is not fixed by this action, then we know that its image by the action has to have the same FPDIM as itself, which means that we have additional information about the FPDIMs of those two simple objects. Yeah, so telling us that this proposition gave us a lot of information about when a simple object X can be fixed. So that was really handy. We also showed that if C is a modular category, and we know the number of invertibles in C and the number of invertibles inside the adjoint component in the universal grading, then we're actually able to determine exactly how many components of the universal grading contain an invertible object. It's the number of invertibles inside of C divided by the number of invertibles inside the adjoint component. And we actually not only know this, but we do also know that the multisets of the Frobenius pair dimensions of the simple objects for each of these universal grading components are entirely identical. So if we look at every single component that contains an invertible object, and we look at all of the Frobenius pair dimensions inside of those components, we know that those multisets for every component are entirely the same. So each of the components that contain some invertible object share a very similar kind of structure in general. This was the general process we used to discard cases. In general, what we did was um, if we're able to discard many cases for a certain rank, then we know that for that rank, the only remaining cases, the remaining cases are the possible are the possible structures for that rank. So for example, for rank 17, if we're able to discard the perfect case, then we're left with just the pointed case, which is what we want to do. So the first step if we wanted to work on a given rank, was to find all possible values of the order of our group G of C, using the fact that the rank of C is this non-negative linear combination of the number of invertible objects in C and the number 8. So as I said, this equation greatly restricts the possible numbers of invertible objects in our category C, and this makes it much more feasible to actually list out all of these possible values. So that's exactly what we do. We list them all out, and then we perform casework on them. For every single possible number of invertible objects, we consider the universal grading of C, and we enumerate all possible ranks of the universal grading components. So we look at what the possible ranks of the components of that universal grading are. And this is, again, feasible because of the result that I talked about earlier. The ranks of the universal grading components must be congruent to each other mod 8. And yeah, this result gives us a much smaller list of possible ranks of the universal grading components, and we can once again perform casework on them. So when we do perform casework on them, we first start by discarding as many cases manually as possible, because using manual results is obviously easier and faster than running that whole algorithm. So these results, for example, are these two propositions that we talked about in the previous slide, and results kind of similar in flavor to these two propositions. Then we are left with some cases that we weren't able to discard manually. So what we did for those is we ran the basic algorithm. So if this basic algorithm does finish in some reasonable amount of time, then it outputs some possible cases for the Frobenius pair dimensions of all the simple objects inside of our category. So then what we do is we can work through all of those possibilities case by case. And usually those Frobenius pair the Frobenius pair dimensions obviously give us a lot of information. So usually we are able to discard most of them. Now, as I said, for higher ranks, the basic algorithm doesn't always finish in a reasonable amount of time. So if it doesn't complete, then we instead run the adjoint algorithm. And the adjoint algorithm does give us less information because we only consider simple objects and the adjoint component. But again, this is usually sufficient to discard many cases anyways, so we work through them to discard them. So these were the results that we managed to show using this process. So these are the three main theorems that summarize kind of the main results that we had. We had a few more broader results for some ranks that weren't as restrictive, but that they are enlisted here. So the first theorem that we showed was it answered the main motivating question that I presented at the beginning of the seminar. So it states that all odd-dimensional modular categories of rank 17, 19, 20, and 23 must be pointed. So we did successfully discard the case that of the perfect case for these ranks. So in combination with the result that Chanky and Plavnik showed in their paper, that odd-dimensional MTCs of these ranks must be pointed or perfect, we completed the classification of odd-dimensional MTCs up to rank 23. And this actually does also show that the example of the non-pointed odd-dimensional MTC shown in the paper by Briard and Rowell that we discussed in the beginning of the talk is the lowest ranked non-pointed example of an odd-dimensional MTC. Then we also showed some results for rank 25. We showed that all odd-dimensional modular categories of rank 25 must be either pointed, perfect, or equivalent to this non-pointed example that I just mentioned. So we discarded all other possible odd-dimensional modular categories. So what's interesting about this is that if we do successfully discard this perfect case, then we are able to classify all odd, then we have successfully classified all odd dimensional modular categories of rank at most 25 and 25. We also showed that all odd dimensional MTCs of rank in this large set must either be pointed or perfect. So it was the same result that Chinky and Plavnik showed for rank 17 to 23, but for higher ranks. So again, if we do manage to discard the perfect case for these ranks, then we have completed the classification. And one interesting thing to note for these cases is that in many of the remaining ranks that aren't listed in the set that are more open than just pointed or perfect actually have rank that are congruent to 1 mod 8. For example, rank 33, rank 41, rank 49, and so on. And one potential reason that explains this is that if we take the center of any odd-dimensional fusion category, its Frobenius parent dimension must be congruent to 1 mod 8 because it's the square of some odd number. And because the FPDIM must be congruent to the rank of any fusion category, this means that potentially for odd-dimensional modular categories of rank congruent to 1 mod 8, there are potentially more examples of categories like that that are actually existing that are not pointed. Yeah, that's an interesting thing to look into to see whether there is a pattern like that that potentially shows up. So next, I'll get into some recent results in future directions that could be interesting regarding this. So the first one was that recently it was shown that every perfect odd-dimensional modular category of rank at most 25 is trivial, excluding 21 modular types of rank 25. So this is really interesting because it makes progress towards classifying all odd-dimensional modular categories of rank up to 25, including 25. So it makes progress towards classifying them of rank 25. So as I said, the only case that remains for rank 25 is this perfect case. So what this result does is it reduces the possible types of this perfect case down to 21 modular types. And if we are able to discard all of these modular types, then we have successfully classified rank 25 odd-dimensional modular categories. Additionally, it was also recently shown that if C is a modular category with Frobenius parent dimension that's congruent to 2 mod 4, then C can be factored into first an odd-dimensional modular category and semyon, which is the rank 2 pointed modular category. So this is really interesting because it states that the classification of modular categories that have FPDIM that are congruent to 2 mod 4 actually depends on the classification of odd-dimensional modular categories. And this can be seen using this theorem, which is an application of our results, that states that all modular categories of dimension that are congruent to 2 mod 4 that are of rank at most 2 times 23 equals 46, all of those MTCs must be pointed. Here are also some conjectures that are potentially interesting to carry into future directions. These 4 conjectures are actually all equivalent to showing the first one. And this is really interesting because the first one is that all odd-dimensional and modular categories cannot be perfect. So if this conjecture can be shown, then all of these ranks, so 25 and then all the ranks in this set, would be fully classified because we've classified them except for the perfect case. So if we can discard that perfect case, then we've finished the classification for those ranks. It was shown that this conjecture is actually equivalent to showing that odd-dimensional modular categories are solvable, and it's equivalent to showing that odd-dimensional fusion categories are solvable in general. Finally, if we also use this last result that was shown here, that modular categories of the FPDIM 2 mod 4 can be factored into an odd-dimensional modular category and some other and semyon, then this conjecture is actually equivalent to showing that modular categories of dimension not divisible by 4 are also solvable. So carrying the future research in this direction would also potentially be really interesting. So any progress on that would be very, very cool to see, because it would continue showing the classification of those ranks that were left open. And that's all I have. So thank you for listening.
Thank you very much. Very, very nice talk. So any question from the audience or online? Yeah. So let me start to ask. In fact, I wanted to ask about, can you hear me? Yeah. Yeah.
Yep, I can hear you.
About the rank 25. So you talk about that at the end. So,
Yes.
So you talk about this list of 21 remaining type. So did you try to look to this list and to see whether some can be ruled out by hand or something like that? Or...
I actually did take a brief look at the modular types, and I believe that if you run the algorithm that I used on these modular types,
Yeah.
you can potentially restrict these modular types even further. I don't quite remember the number of them, but if I remember correctly, you can get it down under 20 modular types.
Okay.
So yes, there is potential for that.
Okay, okay, nice. Okay, so another question about I would like to hear your experience at the MIT Prime program, in fact, how everything goes. Can you talk a bit about that?
Yeah, so MIT Primes has been a really, really great experience. So essentially the way it works is I found out I got in and then I was paired with my two mentors, Augustina and Professor Julia Plavnik, which was really, really amazing. They've been really, really great mentors throughout the whole process. So after I found out I was paired with them, I uh, I did some background reading on this research because obviously I hadn't seen like this fully niche research area yet. Um, so I spent a few months doing reading on so I could actually understand the research question. And after that process, then I actually started the research itself. And essentially, yeah, the process was I would conduct research under weekly meetings with Augustina and Julia, um, and and we would just move forward with it as as we could. So it's been a really amazing experience. Obviously, thank you to Augustina and Julia for being such amazing mentors. Um, and yeah.
Okay, very, very nice. And what about your future? In fact, would you like to do research in this topic in the future, or what do
I'm
you?
not 100% certain yet. Um, I'm obviously still in high school, so there's a lot of time for me to decide. But this has been really, really interesting. So I think it would be quite interesting to go into actually this field. But yeah, obviously I haven't decided yet.
Sure, sure. Okay. So, let me check. So people online can write online or can unmute themselves if they want to ask some question.
Oh, do you know in our list, what is the largest dimension of these categories?
Can you hear the question? Did you hear the question?
I couldn't hear that, sorry.
Okay.
He will move.
So what is the largest dimension of the categories in your list? For each, let's say for rank 23, what is the largest dimension? So is there a relationship between the largest possible dimension of the MTC and the rank?
Oh, Did you ask about rank 23 in particular, or did you ask about a
No,
general
I'm
rank?
asking for a pattern. Do you see any pattern between the largest possible odd dimension and the rank?
When I was looking at it, I didn't see any specific patterns.
So growth rate.
When Sorry?
Let's say some growth rate, because we're interested in finding a relationship between the rank and the dimension or the largest fusion rule coefficient. But in your case, apparently the fusion rule coefficients are 0 or 1. So, what I want to say is I want some pattern between the rank and the dimension, even with some restrictions. So it's let's say growth rate maybe.
Yeah. I don't quite remember exactly what the actual dimensions were, because we generally weren't too concerned with the dimensions, and we were in general trying to actually focus on discarding them.
Yes.
But I do remember that they did, for many of the cases, they did get quite large, if I remember correctly.
I see.
Um,
So for
yes.
23, do you get something like 1,000, maybe more than 1,000, something like that?
For rank 23, we didn't actually end up with any physical categories, because when we ran the algorithm, ran it specifically for the perfect case, and the algorithm produced no output, because the perfect case cannot exist. So it didn't produce anything. So yeah.
I see.
So for rank 23, the dimension is always 23 because it's pointed.
Right. Yeah, one reason I'm asking is if you know the relationship between the dimension and the rank, probably you can find a way to get some rank finiteness results for general fusion categories, right? For very spherical fusion categories, because you can take the double or center, trivial center, you get the MTC, and you can look at the rank of the MTC and the dimension, something like that. Right. So yeah, that's one of the motivations. But yeah, thank you.
Yeah.
Any other question? Okay, so if not, let's thank the speaker again.
Yeah, thank you for inviting me.
Thank you. And see you later. Sure.